So let's look at another sort of nice but daunting feature of standard ML, which is sort of the restriction on recursion. And now, hey, it's a restriction. How is it nice? There are two things that I think, in my mind, you know, reduce the negatives of that and increase the positives of that. So the first is many functions are better defined recursively. The second one is standard ML uses compiler tricks, basically, to allow for recursion to be efficient. So, we have here this C program, pretty bog standard looking, recursion, uh, factorial. Let's not get ahead of ourselves here. This factorial function, and let's run it. Compile, let's run, and it does not give the factorial of 5, it gives a factorial of 4, so obviously there's this off by 1 error. That off by 1 error, you think, hey, that's a pretty, it's pretty easy to spot, but it's also pretty easy to make, because you're often putting in for loops, I is less than some value, but in this case it should be less than or equal to. Right? The for loop doesn't really need a lot of this stuff. You can actually admit some of these clauses. Uh, these clauses can be a lot of things. You can, instead of I plus plus, you can have I plus equals to 1 or I is equal to I plus 1. All sorts of ways you can make a for loop that does all sorts of different things or does the same thing. But you tend to use it in a certain way all the time, which can lead to you tripping up. So just to be sure, let's compile it, and I guess it didn't work. We actually forgot to change it. That's always fun. And now it works correctly. So let's move on to the standard ML part. So you see here that this top factorial function, there's actually two. I'll get to the second one. Is very close to in fact, it's pretty much exactly like the mathematical definition of the factorial of 0 is 1, the factorial of 1 is 1, the factorial of x is equal to x multiplied by the factorial of x minus 1. So just to be sure, let's compile it. It gives a compiler warning because standard ML's compilers tend to be very strict for it because it's very strictly defined, but it works. Now let's actually look at the second function because it gives some insight onto how you can make recursion efficient. Now, but before even that, let's say, hey, we have a function defined inside another function, and you can do that. You can do that in Python, but what it allows for here is functions that don't make sense outside of the function you want to use it in. So here you have basically this factorial function with two arguments. And what it's doing, it has this accumulator and the value that gets decreased every time, as seen here. So the idea is that the last thing being called, the last operation, is the recursion itself. So here it isn't. It takes the recursion, the the recursive call, and then multiplies it by x. This does the recursive call last, so it makes it what's called a tail call. And what can happen behind the scenes is, if the compiler supports this, is that can change, basically unroll the recursion and make it iteration once it's compiled, because all it can do is take the function that's already been called and just change some values and run it again. Basically, it's called tail call elimination. So basically, by doing this, we can get the best of both worlds. We can get the naturalness of recursion with the performance benefits of iteration. So let's look at another example. This is, I'm using, very standard basic, mathematically defined functions because they're very easy to, understand. But I mean, they also, really show why you might want standard ML type syntax. So this generates the Fibonacci numbers up to n, so it returns a list of size n plus 1, and similarly, we have this function that really only makes sense inside of here, and it basically generates the reverse of the list. In this case, I found it easier to get the reverse and then reverse it. It's not the most efficient way to do this, but it is the most asymptotically efficient way to do this, since it's a linear time function and we have linear size output. So what we really want to look at here is down here. So what we're because it has a couple of things. First of all, it has in here there are a couple of anonymous functions, and second of all, you know, there's a great example of why anonymous functions are so great. Anonymous functions, by the way, are also called lambdas. So, standard ML, the standard ML of New Jersey system has, at the very least, has a library function called map. What map takes in is a list and also a function that is of type, basically the input type of the function is of the type of a list element, and it outputs, and it could output any type really. But the idea is, if you want to take a list and multiply every item in the list by 2 and return it, you can just have this simple anonymous function, and this anonymous function will be applied to every item in the list. So it's a very nice thing because instead of having to iterate through the entire list yourself, you can just say, apply this function to every item in the list. And you see here we call fold L, which does a similar thing, except what it's doing is it has this accumulator value, and basically you have this accumulator and you are modifying the accumulator as you go through the list. So basically, what fold L and map are basically sort of functions that iterate through the list for you and apply what you want to apply to each item. So instead of having to manually make a loop, you can just use these functions, and what you would want to put inside the loop, you're instead passing as an argument. You can pass it as an argument very easily because you can just make an anonymous function, which is very compact. It's not like in Java where you can, well, I'll get to some newer features of Java later, but in Java 7, the only way to sort of fake this functionality is either have an anonymous class and just having a class definition as the argument of a method is very unwieldy, or you could have a non-anonymous class and defining something you're only using at one point in the code somewhere else is also very unwieldy. So it basically allows for very compact expression of what you want to do. And, very readable, much more readable than Java's anonymous classes. So as you can see, what we wanted to do is get the first few terms of the Fibonacci sequence, and then multiply it by 2, and then print it out, and that's what we did.